is capital T, and the period is 1 over the fundamental frequency. I think everybody understands this, but it's important. If you don't understand, don't feel bad, just make sure you understand from here on out. I'm trying to get rid of the bad markers. So that's the case. Now this, it's from the 50% point here to here is tau. And the ratio of tau over T is actually equal to the duty cycle. You've had this before in your, I think it's in your digital electronics classes. I'm not sure if you had it, where else you had it, but duty cycle is very common. It's the amount of time the waveform's high versus the total waveform. It's a square wave. And, well, this is a pseudo-square wave. So when we do this, go ahead with the specifics.
So it says to determine the value of the capacitor at the fifth harmonic.
Yeah, okay. Let me draw the circuit.
Okay, yeah.
Is there a resistor here?
Yes. Which that's 1 kilohertz. Or kilo.
And just see, we'll get to the values.
Mm-hmm.
Well, you can tell me, what is R?
They're both 1K.
1K ohm.
Mm-hmm.
And C?
C is, you're supposed to determine C, which, okay yeah.
A certain level of attenuation, right?
At the fifth harmonic is reduced 20 dB.
All right, now this is kind of one of these things, you don't even need the waveform information. The only thing you need is the fundamental frequency. Y'all hear me on this? They want to know the value of the capacitor so that we reduce the output by 20 dB, right?
Yes.
Y'all hear me? So let's think about that and do it. This is the input, right? This is the output. The transfer function, this is perfect for what I'm about to do. The transfer function of this thing with no capacitor, so it would just be R, would be equal to R over R plus R, right? And that would be the ratio of V out over V in. Make sure everybody understands that. Y'all agree with that? Output voltage is two resistors in series would be what? Voltage division. Forget the capacitor now. It's out of the circuit. This is the actual transfer function of this circuit, assuming the capacitor isn't there. Because we need the value at the fifth harmonic before we insert the capacitor in order to have a 20 dB reduction. Do you all agree with that? With me? All right. So this is going to be just 1/2, isn't it? You all agree? That's the output. Do you agree with that?
Do you mind saying that part one more time, the 1/2?
Yeah, sure. If we just have these two things, right, then we want an output over input. Input is VI, output would be VI over,
Oh, okay.
because we have R and R here, right?
Gotcha.
Now, what's the transfer function with the RC network, with C in there? Well, now, here's the way I'm going to do it. This is so perfect for what I wanted to cover today. I'm so glad you asked that. I'm going to call the combination of these two impedances, just call it ZRC. Right. Now, you know, as electrical engineers, these things are second nature. If we wanted the impedance of that, those two in parallel, the way I always do it when I have components in parallel, I'll say that ZRC here would just be 1 over the first impedance. I'm going to put R first. 1 over R plus, and then it would be SC. Do you agree with that? I'm using S instead of J omega. Okay? Now when I look at this, the transfer function for this is what? Well, it would be this impedance, right, divided by ZRC plus, and then R. And again, that would be the ratio of output to input voltage if we did the combination of those two impedances together. Do y'all agree? Okay. In the back. Nathaniel, are you with me?
Yes, sir.
Okay. Now if I have that, this is the way I typically do it. I try to simplify things, make them as easy as possible. I know this one ahead of time. I got ZRC and top and the bottom. I divide top and bottom by ZRC. So I get this. Do you agree with that? With me? All right, now I'm going to go ahead and expand it. So now I have 1 over 1 plus r, and what is ZRC? Well, this is ZRC, isn't it? 1 over that is just 1 over r plus SC, isn't it, class? Do y'all agree with that? I'm just making sure everybody's got to make sure you didn't make a mistake, and I'm glad you're doing it. Now, what do you see happening here? Well, multiply through by r. R times 1 over r is 1, right? And r times SC is SCR, isn't it? You agree with that? Nothing tricky here, it's just multiplying. Now what am I going to do? I got how do I shut this thing off? I inherited my wife's phone. I had an Android, now I have an iPhone, and there's a little thing where you thump the switch, the on-off switch, and it mutes. All right, so now I'm going to just put this as 2, right? Now the next thing I'm going to do is figure out what the magnitude of this is, because really I'm going to get a magnitude of a ratio, and you're going to see this in a second. Well, what's the magnitude of this? 1 over 1 plus 2 plus SRC. Here we take S and we make it J omega, don't we? So when we look at the magnitude of HRC, it's going to be 1 over the quantity, and it would be 2 squared plus omega RC squared. Do you agree with that? Do you all agree? That's just magnitude, isn't it? Square the imaginary, square the real, take the square root. And by the way, you never square J, because J is simply an indicator that it's at 90 degrees. The phase is 90 degrees different on the capacitor and resistor. So and I will see people do that occasionally. All right, now what is this really? Well, that's V out, right, over Vn. And this is V out over Vn, right? So what's 20, they said 20 dB, fifth harmonic?
Yes, it's reduced by 20 dB.
All right, so what is 20 dB in terms of an output voltage ratio? That's what we're looking for. So if we have 20 dB on that side, well, it's got to be dB this side. Since it's voltages, it'll be 20 times the log, right? It would be 10 if it was power, but we're working with ratios of voltage. And then it would be the magnitude. Now they want a 20 dB reduction. So now you take the magnitude of this guy right here, V out over Vn. You know what? Yeah, I can just say that if I want, normally when you say 20 dB reduction, you take the value of the input without any filtering added. It would be this. So you take V out over Vn without filtering is 1/2. Isn't it, class? That's the ratio. And if you want to think about, well, that's not the output voltage, multiply 1/2 by Vi. Do you agree that would be the magnitude of the output voltage with no capacitor added? Agree? We want that reduced by 20 dB, so we divide it by that guy, which is going to be 1 over the square root of 4 plus omega RC squared. Now just listen to me on this, right? Are you with me so far with what I've done? Because remember with dB, it's always, if we're talking about voltage, when we talk about dB of anything, that's 20 times the log of the ratio of voltages, V1, V2. In our case, V2 is with the filter, V1 is without. And remember, this filter is going to reduce, so in order to get a positive value for dB, because they said positive 20 dB, it's always that way. You've got to put the filtering voltage below there because it's going to be less, right? So if you have the ratio of something divided by something less than it would be greater than 1. and therefore the log would be positive. Do you follow me on this, class? With me? All right, so what happens here? Well, we can find out what this ratio is. Do you agree with me? Let me just do this. Jake, you asked this. Does this answer your questions?
Yes.
If you have a question or you don't understand something, just say it. But I'm trying to be clear about this. Logarithmic stuff, occasionally when they talk about dB reduction, people get a little misled. This is the easy way to do it. So I'm going to divide both sides by 20. Right? Remember, there would be a v in here. These are going to cancel. The v in, that's why you only worry about ratios, transfer function. If you want a reduction, you don't care what v in is. The only thing you need is a ratio of the output with and without the filter. The filter is the capacitor in this case, just so you know. All right, now what happens here? Well, that's going to be equal to 1 equals, well, really, what do we do? We take both sides to the level e, right? Right? Actually 10, sorry, this is log base 10, so it's 10 to the 1, right? Because it's log base 10, is equal to, in this case, it's going to be 1/2 square root of 4 plus omega RC squared. Now, so I can get rid of that 1, right? Okay? Okay. All right, now I'm down to here. I'm going to multiply both sides by 2, because I got an F. I could bring it inside if I wanted. I'll tell you what. Now, if I take that inside, what do? If I take 1/2 inside that square root term, I have to square it, don't I? So if I square that, I'd get 4, wouldn't I? You with me? So if I bring that in and square it, I would get 1 here then, right? And it would be plus this divided by 4. This might be easy. Do you agree with me?
You got the 10 raised to the 1 because it's 10 raised to 20 over 20 to
This
convert
is
it.
a log base 10 of A equal, all right, something, call it B. Well, if I want to get both sides, get rid of that logarithm, I take what, 10 to the B, right? Or excuse me, 10 to the power B, right? Would be equal to A.
Okay.
Because it's not log base E. If it's log base E, then you got to take E to that value. But these are all log base 10s. And if I'm not clear on that, understand LOG to me has always meant log base 10. In MATLAB it isn't. And in mathematics courses and some physics courses, if they don't put an LOG 10, you assume LN. But I like LN for natural log, LOG for base 10. That's the way I've always had it when I was young, but nowadays there are, in the mathematics department especially, there are adjustments. All right, now we're down to that. All right, do you all agree with what I've done so far? We still haven't got omega, right? Or C. Omega is going to be the fourth harmonic or fifth, what?
Fifth harmonic.
Fifth harmonic, no problem. We know what we know F naught is 1 over T, and that's equal to 10 megahertz, so then omega naught would be 2 pi times 10 megahertz. And therefore, the fifth harmonic would be 5 times 2 pi times 10 to the, or 10 megahertz. So when all is said and done, what I'm going to do now is, well, how am I going to solve this? I'd like to produce breakout omega RC by itself. So now what do? It's pretty straightforward. Just square both sides, right? You all agree with that? Mm-hmm. We square both sides, we get this. Agreed? Now, technically, we should subtract 1 from both sides. You don't have to do this. These are too close. And you would get 99. Agreed? And then what are you going to do? Well, you could multiply by 4. You notice that's about 400, isn't it? I'm going to make it 400. You don't have to, but I am. And now I have omega RC, right? I'm after C, but that's still squared, isn't it? So what do? Square root of both sides. And we'll just leave it like that. And then I divide it by R, right? And I've got R. and I divide it by omega. But what omega? The fifth harmonic. That's what he said, right? And what's the fifth harmonic going to be?
50 megahertz.
It's going to be R times, well remember this is omega, 2 pi times 5 times 10 megahertz or times 50 times 10 to the 6th. Do y'all agree with that? Now Jake, you got a calculator or somebody got a calculator? This is how you do business here. If you take a look at this, R in this case is equal to 1,000. So I have 1,000 down here, right, times 2 pi times 50 times 10 to the 6th.
It would be 6.36 times 10 to the power minus 11.
That's what C is?
Yeah.
Okay. So C would be, say it again,
6.3 times 10 to the power minus 11.
10 to the minus what?
11.
11. All right, it's 63 picofarads. What's the answer?
That's right.
Now, do y'all follow me how I did that? That's a very common thing. You see the waveform made no difference. You just have to know the fundamentals. The rise time, fall time didn't make a difference. Now, what's typically done now, if you want me to take you to the next step that I would ask, so everybody knows, when I say I would ask, probably it means I will ask. All right, probably. I can't give you a better hint. What I'd say is, all right, you've got that capacitor. We're assuming this capacitor. Now listen to me. And now, what I want to know, I'm going to erase all this right here. I'm going to leave that waveform as the same rise time, fall time. Now I have the capacitor, but what I want to know is the value of an output, and this is going to be the envelope method. I showed you the maximum value of the output. In other words, it's an overestimate, if anything, or excuse me, an underestimate. Sorry. It's the maximum possible value. Filters generally reduce things. All right? So this is going to be, if everything was as bad as it got and we hit the actual peaks on all those sync functions as you go down, then this is the output you get. So if I have my input right here, this is the square wave thing, plus the minus voltage V here, it's 5 volts. Then I put the resistor R, that's 1K. I've got a capacitor here. The capacitor is that value, 63 picofarads. So now I'm going to just put it as C here. Then I have a resistor, 1K. And here's V out. Now listen to me. And that's Vn right here. Now, I would ask, using the envelope method, that's the method where the first and second time constants cause really the rise time, or the value of tau, and then the rise time determine where they are. Find the output voltage at a certain frequency. And say I say the output voltage at 6 F naught. You with me on this, class? Not F naught, but 6 F naught. So let's just sketch this. First we sketch the input. Or we could, I'll tell you what, we'll get the output at 5 F naught, because we've already got the capacitor. It's a 20 dB reduction in input signal, right? That would cause that, but it doesn't say anything about the waveform, right? Whatever the input signal is, if you're at 50 megahertz and you put that capacitor in, then the input signal will be reduced by 20 dB. You all follow me? Doesn't matter what the input is at that frequency. Now I want the actual output at the fifth harmonic based on this waveform. So how do we do it? Well, we're going to plot F logarithmically in this case, right? Well, we know the magic points. This would be 1 over pi tau here, and the second point would be 1 over pi tau rise. Do you all agree with me? This is such a good problem. It showcases everything. You calculated a capacitor, you get a certain level of attenuation. It's called shielding effectiveness. And now, we're going to plot this. This is just the input waveform here, so this is going to be just input. And that's this way. I start up here at what? 2 times the log, well, 2 times, I'll tell you what, I output here in dB microvolts. So this is going to be what? 20 times the log. Remember how we did this? And now it's going to have what? 2 times the duty cycle, which is 1/2, right? Times the magnitude, which is 5. But we have to divide that by 10 to the minus 6 because I want dB microvolts. You all with me? So then I divide this by 10 to the minus 6. That's going to give us our base level here. Now the first frequency is what? Well, what is tau? I know that what? T was 1 over 10 megahertz, right? 1 over F naught, or 1 over 10 meg, which is 10 to the minus 7 seconds, right? Since it's a 50% duty cycle, tau would be T over 2, or it would be what? 5 times 10 to the minus 8, right? You all agree with that? All right, now multiply that by pi, and then take 1 over.
6.37 megahertz.
This is 6.37 megahertz? Okay. All right, where's this one? The rise time was 10 nanoseconds, is that right?
Yeah.
You see how that had nothing to do with this problem at all? I mean, the first problem. So what's this going to be? 1 over pi t rise.
31.83 megahertz.
All right. You agree? So we start here. We'll get that value in a second. At this frequency, we start going down at minus 20 dB per decade, right? Then we hit this frequency, and then we go down at minus 40. All right, now the fundamental is what? 10 megahertz, right? That's down here. That's 10 megahertz. But we wanted the output value of voltage at the 5th harmonic. That's what I should have said right from the, because we've already calculated the dB reduction of filter width, right? So what's that going to be? Well, the 5th harmonic is out here. That would be 50 megahertz. Do you all agree with that? How many do here? You with me? I'm not trying to go fast. You got me on this? All right. All right. Now, if we want the value of the signal out here, add 50 megahertz out here. Well, this is not drawn very well, but let's say 50 was back here. What I have to do to get the, now we're after the output voltage, but we're going to find the value of the input voltage at that frequency. Do you all follow me? The component, the value. So now we're going to say Vn at F equals 50 megahertz would be equal to 20 log of 2 times 1/2 times 5 divided by 10 to the minus 6. That's like 133, I think. 133 dB microvolts. You can correct me on that. Then it's minus 20 times the log of the upper frequency, which is 31.83 over the lower, which is 6.37, right? And then we get to the higher one. Then it starts falling down to 40 dB per decade. Do you agree with that? 40 times the log of what? Well, the output of 50 megahertz. Yeah?
50 over 31.
That's right. 50 over 31.83. And that would be the input's value of voltage at that frequency. Now, what's this? It's what? 5 over 10. So 5 times 10 to the 6, take the log of that, times 20. It's like, is it 136? What is it? Did you get a Jake or not?
I did it with, not in microvolts, I did it with just regular volts.
No, give it to me in microvolt. Well, microvolt's
I
10
got
to the 6.
133.9.
Yeah, that's about right. 133.9.
Yeah.
So this is 133.9 dB microvolts minus, what's this next one? 20 times the log of this is, 18?
17.9.
What is it?
17.9.
Thank you. Minus 17.9.
13.
And then what about the next
It's
one?
13.9.
13.9?
Yes.
Okay, hold on. 13.9, what about this one? $7.85. All right. And this is dB microvolts. Now do the math on this whole thing. Subtract 13.9 and 7.85 from 133.9.
That comes out to 112.16.
So that's the signal strength in dB microvolts at that signal that we're putting in there at the fifth harmonic going in. Y'all follow me? But we've already calculated what value of capacitor we call the output to go back down by 20 dB when added, right? But that's not quite the way it works because what? First we calculate the output without it, right? Right? And we had 1/2. You all remember that? Then we added the capacitor to calculate. So actually our value, in order to get the actual, and this is the reason I'm saying this, and I'm trying to be emphatic about this and make it clear. In order to do this properly, you've got to recalculate what the transfer function's value is going to be on this one. And remember, your output voltage, that's the input voltage right here in dB microvolts, right? So let me erase this and finish this, because this is a big problem. Now, when I take a look at this, and I want the output of the system, first I need to know that V out, just watch this, is going to be V in, whatever the input voltage is, times the transfer function, right? Times H of omega in this case. Do you all agree? H is just the ratio of input to output, right? In our case, we went through it and we knew that V out would be equal to V in here times what? When we did the math on that one, our output volt, remember how I did this? I said that this was ZRC, and I found out that the transfer function H was ZRC over ZRC plus R, right? And then I divided top and bottom by ZRC, and I ended up with what? 1/2 plus SCR. I'm just going through this to make sure everybody's clear. Remember me doing this? And then I replaced S with J omega, right? And then I got the magnitude of this. So the magnitude of that transfer function would be equal to 1/4 plus, and here, since it's the fifth harmonic, it would be 5 omega naught R times C, right, squared. And that would be the output, right? Now, I'm going to make a point. Remember, that's the output linear. That's just the output voltage, V naught, if you know the input voltage. You agree with me? If we want to put this in terms of dB microvolts, and you'll see why. First, is everybody with me here? Everybody's writing. Or a lot of people are writing. I'm going to give you a second to catch up. I'm not trying to scream through this. Okay, ready? Okay, everybody? So what happened? Well, if I want output voltage in dB microvolts, I have to take 20 times the log of the magnitude of V out over 10 to the minus 6, right? All right, now just watch what happens. So I'm going to say V out in dB microvolts would be equal to 20 times the log, that's a base 10 log, of magnitude of Vn times 1/4 plus 5 omega naught RC squared, right? I'm making out just the fundamental radians. So what happens next? I want to make sure you all see this. Just take a look. Well, if I have the log of two numbers, what is log, I say this over and over again, of A times B, anybody? Isn't that just log of A plus log of B? Isn't that right? I mean, do it for yourself. Make A and B, say, 100, right? You got 10 squared, 10 squared, 10 to the fourth. Log of 10 to the fourth, 4, right? This is base 10. Are you all with me? I don't want to look. So now do it this way. Well, what's the log of, if A is 100, log of 100 is 2, right? Plus log of B was 100 is 2. 2 plus 2 is 4. Y'all follow me? I'm just trying to really underscore this fact, because there's people that sometimes don't see it. And I'm not going to ever say anything bad, because I don't see things too, especially when I play chess. All right, so y'all agree with that? Now, next, I'm coming to here. Well, you see I have the log of Vn, but I didn't put this thing divided by 10 to the minus 6 here, so it should be times 10 to the minus 6 down here, right? Times the whole thing. And there should be divided by 10 to the minus 6 here, so that what? When I expand that, I get 20 times the log of the magnitude of Vn over 10 to the 6th. This would be at the fifth harmonic, right? It's that. Then it's going to be plus 20 times the log of the magnitude of that transfer function. Now I'm going to show you something. You see how many it expands from there? 20 times the log is just Vi over 10 to the minus 6. Then we have 20 log of this. Well, that's log of 1 minus the log of the lower one. Now, so just so you know that, I'll leave it in terms of just a ratio of things. So it's plus 20 times the log of 1 over the square root of 4 plus, and then it's going to be what? 5 times 2 pi times 10 to the 7th, right? Times r, and r was 1,000, right, or 10 to the 3rd, times c, which is 63 times 10 to the minus 12, right? Gotta take that mess and square it. Do y'all agree with that? So what do you, when you do this, what happens here? I can't tell. You're gonna have to tell me. What's 1 over the square root of 4 plus all that business squared? Because I can't do that in my head. You got 10 to the 10th, 10 to the minus 12th. That's 10 to the minus 2, 10 to the minus 1. It looks like this is going to be 1 over the square root of, I don't know actually. Can you give me that value?
Working on it.
Y'all with me on what I've done? And this will be the level of the output signal. And it'll be more than 20 dB less than the input. The input at that point was 112, right? You would think it would be that minus 20, right? Because remember, when we calculated the first value, we had R's in there. We got a factor of 1/2. So it's going to be 3 dB less than that.
I got, oh wait, no, 2 pi, sorry.
You get like 0.09.
For what?
Oh,
For what?
never mind.
I got 50.26 times 10 to the negative 3.
Is that the whole 9?
Oh, no, but that's just for the thing inside the,
Oh, yeah, do the whole thing.
Yeah,
This
sure.
is going to be what? That's the signal right there, 112, right? 112.16 dB microvolts. That's the input value of voltage at the fifth harmonic, right? If you look at the spectral domain, that would be the signal strength level in voltage. Now, take that, and what do? We subtract whatever this is, and I don't know what that is, to get the final answer. And he said the second one's around 50, did you say?
Yes, so it's gonna be, all of it is 138.13.
That doesn't make
That
sense.
doesn't,
This is negative.
yeah.
This should be, log of 1 is just 0 minus 20 times the log of this whole mess squared. So it can't be higher than these. It's not going to be a gain. It'll be less than 112.16 dB by probably a factor of at least, I'm going to guess 30 or 40 dB, but I can't tell you off the top of my head. At least 20. No, about 21, no, 23 dB.
132.
That's not believable, because see, it's got to be minus some, see, this is going to be what?
I got minus 26 dB for the
All right, so take minus 26 from 112,
86.2.
86.2 dB microvolts. Now, what did you say you got, minus 26? All right, I want to make this point. We calculate the value of the capacitor so the input would be down by 20 dB, but the input without anything was 1/2 the actual input, right? So when we figure out the total attenuation, we're going to get at least 20 dB, more than that. 20, you got,
I got that as well. 86.18.
how many dB is that? That's 26 dB, right? What value did you get for this thing?
I got,
Minus what?
Minus 26.
Right, point what? Just minus 26 dB?
Yeah.
I got minus 25.97.
That's what I got.
Minus what?
Minus 25.97.
26.
26.
All right. With me on that? That's how you get the output. That would be the maximum value of the output. Now, there's a lot of people who make mistakes along the way on a problem like this. But I hope I showed you how to think about it. Always look at the value of the input signal at the frequency, 5th harmonic, 6th, 7th, 8th. Then find the reduction at that frequency the filter causes. All right? You with me? And the nice thing about dB is this. If I got an input signal strength of 112.16 dB microvolts at that frequency, and I know I want to make sure I have isolation or shielding in the next stage. I don't want any of that. What I can do is design a filter so maybe not 20 dB. If I've got, it's another good question. How far down does this have to come before it's not a problem? It depends on the circuits, but generally if you get 60 dB of attenuation, pretty much it's dead, all right, for most things. 60 dB is a huge amount. And you're already down that far, so 60 dB if you just think about it. 10 dB is a factor of 10. 20 a factor of 100, right? 30 a factor of 1,000. What's 60? Factor of 1,000,000. 60 dB is it's a huge amount of reduction in signal. All right? You got another question for me?
No, that comes in.
That kind of covered everything.
Yeah.
That did the whole 9 yards. A lot of times the problems with people try to do is if they see a rise time, surely the professor expects us to use it. Don't do that on my test. It's not always that you need to use all the information. Some of it is just extra. In this case, we used it. All right, other questions about the homework? Are you kidding me? Is that what? All right. Well, since that one was perfect for my drawn to shields, now I'm going to talk about shielding effectiveness. Shields can be either physical components, RLCs, and then the shielding effectiveness is called insertion loss, which is how much loss is due to the filtering. Or you could talk about shielding effectiveness in the truer sense where you have a metal shield, basically. Now we did this, and I'm going to go through it one time. If we have a metal shield of thickness D, right, when we look in the frequency domain primarily, We take this thing, we'll turn it into a transmission line kind of problem. But I'm not going to do the whole 9 yards on that. I'm just going to show you something. If we have an incident electric field here, and it's propagating in this direction, and it hits the shield, right? The value of the electric field right on the other side of that would be what? The transmission coefficient of region 1, right? Times the electric field incident strength. Y'all with me on this? You can call it E naught if you want, E naught incident. Now that's the value right here. And we know one thing about it. Well, we know that in here we're going to have some gamma that's alpha plus j beta, right? And that's equal to the square root of j omega mu over sigma plus j omega epsilon. It's got, and if it's a good metal, if sigma's large, it's about it's really about j omega mu over sigma, right? Are you with me on this? Everybody okay with this, right? All right. Now, if that's the case, you're going to have an alpha value. Well, the electric field strength, after it propagates through here and it's reduced by a factor, that electric field strength will be tau E naught incident times e to the minus alpha d. Dr. Wentworth's book always doesn't put alpha there. He'll put gamma, where you get alpha plus j beta, but beta doesn't do a thing. Beta is a phase. Don't worry about it. You got me on this? All right. Now we're not quite done. That's the electric field strength just before you get out of the shield. Then you would have to multiply it by the transmission coefficient in region 2. Do you agree with me? Y'all remember doing this? And therefore, the actual transmitted field would be equal to the incident field strength. Now again, I'm going to do something. I'm assuming this is normally incident. We talked about oblique incidence. It's a more complicated problem. But normal incidence is the way we think about it. Because oblique incidence, the shielding effectiveness is greater. As the thing comes in at a non-normal angle, you get even greater reduction. So they always look at worst case. All right, so it's going to be E naught incident, transmission coefficient 1, transmission coefficient 2, times e to the alpha d, and that would be the transmitted field. Do you agree with me? I'm going to fill in some blanks here. Now the shielding effectiveness, as defined. Is usually just termed SE. Shielding effectiveness is 20 times the log of either the voltage or electric field or H field, not power. It's 20 times the log of the electric field with no shield divided by the electric field with the shield. The reason we do it that way the dB will be positive. If we reversed it, we get a negative dB. We know it's a reduction if we've got a shield. Y'all with me? All right, 20 dB reduction when you're talking about shielding, not amplification. So what's that going to be? We'll take a look at this. Or not, sorry. E no shield right here. If you had no shield, then the transmitted would be the incident. Y'all follow me on that? So with Wentworth's book, he just does this. He puts 20 times the log, Dr. Wentworth's book. E no shield is just the incident. E shield is that. And the E naught incidence cancels. So you get tau 1, tau 2 times e to the minus alpha d. And I'm going to expand this just to make a point. When I take a look at this, this is going to be 20 times the log of the magnitude of tau 1. I don't have a minus sign in there because tau 1 is going to be much less than 1. Then it's going to be minus 20 times the log of tau 2. And then it's going to be minus 20 times the log of e to the minus alpha d. Y'all with me? Can you see it okay? I just expanded that 20 log in terms of the arguments. Now this, you can term reflective losses. It's caused by the first reflection. This, right there, would be attenuation losses. If you got a thick shield, this will be dominant. If you got a thin shield, that'll be dominant. What about tau 2? Do you remember what that value is going to be almost guaranteed? Well, first of all, let me just say this. When we talk about reflection and transmission coefficients, we always talk about eta in the region. If this is free space, it would be eta naught. And this would be eta naught on the other side of the shield, and this would be eta s, right? And do you remember what eta shield is? Square root of what? J omega mu over sigma plus J omega epsilon. Correct, class? Well, actually, I put that wrong here. This is square root of J omega mu times sigma plus J omega epsilon. I'm so sorry. That's what gamma is. And so alpha would be the real part of that. And alpha will be about the square root of mu omega sigma over 2 will be about alpha, but don't worry about that. That's eta shield, right? In general? And that would go here, this is shield. Now, do you remember what the transmission coefficient is right here, tau 1? Anyone? Well, it's 1 minus the reflection coefficient of region 1, right? Or I mean 1 plus reflection coefficient, right? Do you remember that? And what is it really? Well, it's 2 eta shield. It's the value of the impedance you're going into over eta shield plus eta naught, right? Isn't that transmission coefficient? And realize when eta shield is equal to eta naught, it's 1. Everything's transmitted. There's no reflection. Now, what about over here? What is the value of the transmission coefficient there? Remember? It's 2 times the impedance you're going into. What impedance is this? When we're out of the shield?
Eta naught.
Just eta naught. So it's going to be 2 eta naught over eta naught plus eta shield, right? What do you know about eta shield in general, magnitude loss? Usually orders of magnitude less than eta naught, right? So what does that make that value, tau 2, of that? Remember?
Eta naught. Or
Look, I got eta naught here, right? Eta naught here. Eta naught plus something small, right? You get 2. That's my point. So this value right here is not much. Usually the shielding effectiveness has to do with the attenuation losses and reflection losses. You could say that this has to do with reflection losses too, but that would be an unfair. There's a little, not much, okay? You with me? All right. That's shielding effectiveness. If I put actual components, now this is easy to understand. I'm going to finish this thought. Does that make sense? We did this before, right? Y'all remember doing this, guys?
Yes.
If you have a circuit with components and you talk about shielding, you talk about an insertion loss. This is the last thing. So insertion loss is IL, and that's 20 times the log. It's trying to give you a figure of merit of how good your filtering is. Up 20 times the log of the magnitude of the output, V out with no shield over, or let's call it with no filter, over 20, or over the output with the filter. So whatever your output voltage is before you get the filter, you take that and you ratio it with the voltage that you get after the filter, take 20 times the log of it. That's the insertion loss. It's an easy concept, okay? I'm going to give you some homework with that. Is there any questions? I'm sorry I ran. You've got to go work, probably. But any questions about this stuff? I hope I made it clear. Now, I'm going to talk about one more thing in chapter 9, then into chapter 10, microwave. Last thing I'm going to talk about, if you want to do the reading, it's going to have to do with common mode chokes. It's the last thing. Dr. Warner's book is extremely simplifies the whole thing. Common mode chokes are very important when you actually have devices you're creating. You're creating antennas, creating amplifiers. Have you had common mode chokes before, the terminology or anything? Common mode choke stops, if you know, almost all the things we do, we want differential voltages. Like a transmission line has a plus minus voltage, current goes in opposite directions, right? That's called a differential mode. The current is going in a different direction in two wires. Common mode means the current's in the same direction. Now you don't want that, but here's how come you get it. You get them from things like ground loops or when lightning strikes. Now, when you get current in the same direction going to the input amplifiers and all that, it destroys them. Absolutely macerates them. And so, I've got to go through this with you. So we put a common mode choke on, and that will reduce. It'll literally cause this huge impedance for common mode signals. Go ahead.